We live in a world of absolutely astonishing materials. Look around you. You'll see an incredible range of solids and liquids, gases. Go to a hardware store, go to a drugstore, go to the grocery store. You're going to find literally thousands of different materials with distinctive and useful properties. You know, never before in human history have there been so many materials with so many different colors and textures, tastes, smells. What I find so amazing and wonderful is that all the properties of these materials depend on the type and the arrangement of their atoms. In this lecture, after a brief review of what I mean by the properties of materials, I'm going to look at 5 important types of material properties. We're going to look at strength, which includes 3 different kinds of strength. There's compressive strength, tensile strength, and shear strength. Then I'm going to look at thermal expansion, and that's by which many solids change their shape when they're heated. I'm going to want to consider stickiness, what makes a glue sticky and what makes Teflon surfaces non-sticky. Then the 4th property is magnetic behavior. Why are some materials like iron naturally magnetic? And finally, I'm going to look at electrical conductivity. And the underlying theme of all these subjects is that atoms and their arrangements dictate properties. I want to set the stage. Where have we come from in the past few lectures? We began by considering the elements in the periodic table. The properties of elements lead to this periodic table. The table systematizes all the chemical elements, and the elements are arranged from left to right and top to bottom by increased atomic number. Atomic number corresponds to the number of positively charged protons in the nucleus. And so you have vertical columns of elements that have similar outer electron arrangements and thus similar chemical behavior. So the periodic table reveals that certain electron arrangements corresponding to filled shells of electrons are particularly stable. The most stable number of electrons correspond to the atomic numbers of the inert gases. That's in the last column of the table. Those numbers are 2, 10, 18, 36, and so on. Now, the fact that some numbers of electrons are more stable than others leads to bonding. All chemical bonding results from a rearrangement of electrons to achieve a lower energy state. And we saw 3 major kinds of chemical bonding. Atoms can give up, or they can take electrons in ionic bonding. And then a few atoms can share electrons locally in covalent bonding, or a large group of atoms can release electrons in metallic bonding. Then we saw variations of temperature and pressure lead to different states of matter. They're solids, they're liquids, gases, and plasmas. Materials can change state from one form to another, and there are also phase transitions and chemical reactions, which I find especially fascinating. You know, like magic, these processes transform material into something completely different. So you get the silvery metal sodium and this corrosive greenish gas called chlorine, and they explode and they become table salt. White powders and water expand to produce a loaf of bread. A lump of coal burns. It vanishes completely into thin air, producing prodigious amounts of heat in the process. And we saw in the last lecture how 2 ordinary-looking liquids can be mixed, and it forms a foaming polymer with completely different properties. You know, I'm often amused to read about the medieval alchemists. They tried repeatedly, and they failed, to turn base metals like iron into gold and lead into gold. They failed, and people scoff at these attempts. But take a look at modern chemistry. Chemists have learned to turn the most mundane materials like water and air into the most remarkable variety of materials, and they've literally transformed society itself. See, materials are useful because of their distinctive properties. You have color, you have hardness. Materials may be flexible. There's their density, transparency, texture, electrical conductivity, thermal expansion. The melting and the boiling points. I mentioned heat capacity. This list of familiar and sometimes not so familiar properties goes on and on. In fact, any adjective that you can use to describe a material object likely relates in one way or another to its physical properties. Materials are so important to our day-to-day well-being. Anthropologists actually define key periods in human history in terms of the predominant material. So scholars talk about the Stone Age. That was the time of the earliest human tools and weapons. Tens to hundreds of thousands of years ago, humans used a really relatively small number of different materials, and they could be taken directly from the earth, from local plants and animals and so forth. And then came the Bronze Age. Bronze is an alloy of copper and tin. It has to be manufactured in a fire. And bronze was most likely discovered by accident when ore-containing rocks were used to build a fire. the Bronze Age, it turns out, began much earlier in the Middle East. It was about 3500 BC in the Middle East, but in Europe, bronze wasn't used until about 2000 BC. That's 1500 years later that the Bronze Age started in Europe. And next was the Iron Age. That's when new smelting techniques with a lot hotter fires led to the widespread production of iron tools and iron weapons. And again, people in the Middle East developed this technique long before Europe. Iron was introduced about 1500 BC in the Middle East, but only after about 900 BC in Europe. And then the modern age in human history is characterized by this astonishing variety of new materials. I mean, look around you. Your furnishings, it features so many different kinds of inorganic materials. So shiny metal alloys, you've got aluminum and titanium and magnesium and vanadium and other metals that were unheard of last century. And we use lots of different kinds of specialty glass. There's shatterproof glass in car windshields and phosphor-coated glass in your computer screen. We also take advantage of all different kinds of ceramics and cements, stones, building materials. And then also, deep inside your automobile, inside your stereo, inside your computer, there's semiconductors and other materials of the electronic age. And all those inorganic materials, that's nothing compared to the range of the carbon-based organic materials in our lives. I mean, you probably own hundreds of different kinds of high-tech organic compounds. Think about it. There's paints and glues and tapes. There's fibers, all the fuels like gasoline, lubricants, dyes, insulation. There's medicine and cosmetics and soaps and detergents, inks, and just an amazing variety of plastic products, shopping bags to sneakers, all different kinds. But there's a unifying theme in all this amazing variety. It turns out that the distinctive properties of all of these and all the other materials are the result of the kinds of atoms and their arrangement in 3 dimensions and the way they're bonded together. So for the rest of this lecture, I want to focus on the close links between the atomic structure and the material properties of various substances. Among the very first attributes you notice about a material are its strength and its hardness. In ordinary conversation, we might talk about a strong piece of wood or a hard chunk of rock. But material scientists distinguish 3 very different kinds of strength. These are compressive strength, tensile strength, and shear strength. And I want to tell you about these. So compressive strength, that refers to a material's resistance to being crushed. If you push down on an object, if it crushes or caves in like a pillow, it has low compressive strength. But if it can withstand a very heavy weight without deforming, that's like a brick, it has high compressive strength. Materials with high compressive strength must have rigid frameworks of atoms in at least 2 directions that are perpendicular. I like to illustrate this with an ordinary stack of paper. I mean, a stack of paper is not strongly bonded together, but if you push down on it, it's got strong bonds in 2 directions, and the stack has great compressive strength. Nothing's holding the sheets of paper together. By contrast, any material with low compressive strength must have 2 or more perpendicular directions with weak bonds or very flexible bonds. A good example is a sponge, which is surprisingly strong in all 3 perpendicular directions, but these bonds can bend every which way. So a sponge has very little compressive strength. Now, the second kind of strength is tensile strength. Tensile strength refers to a material's resistance to being pulled apart. Tension is another of those words that has a common everyday meaning, but also a rather different specific scientific meaning. When you pull in an object from both ends, it's said to be under tension. And sometimes I think that isn't such a different meaning for some of us in our everyday lives. But anyway, materials with high tensile strength resist being pulled apart. That means they have to have continuous chains of strongly bonded atoms or molecules. And a real common example is just a nylon rope. This is an ordinary nylon rope. It's made of synthetic polymer fibers. There's strong bonds in one direction, and this fact leads to the biggest danger of this kind of rope, the fact there's only bonds in one direction. You see, even a few damaged bonds can destroy a nylon rope. Think about that. You see, just break each polymer strand in 1 or 2 places, and the whole rope is drastically weakened, even though it may look fine. And it turns out that the sun's ultraviolet radiation depolymerizes nylon. It breaks the bonds. The polymer can absorb an ultraviolet photon that breaks the strand. So if you leave a nylon rope outside or use it for too long, it's eventually going to lose its tensile strength. When I was in graduate school, one of my fellow students was killed in a rock climbing accident in Wales. His nylon rope, his favorite old nylon rope, broke, and the fall was only 30 feet, but was enough to kill him. So make sure you place your nylon ropes every so often. By the way, this story underscores a key point about strength. Seemingly minor defects can drastically reduce a material's strength. And you probably noticed this effect in glass that has a slight scratch in it. My car windshield, I was driving along the Beltway recently, and I got a slight dent, a nick from a flying pebble. And sure enough, within a few days, a crack spread across the entire glass, radiating from one side to the other from that point where they got the damage on the glass. And the same thing's true for all kinds of materials. That's why it's so very important to inspect all kinds of load-supporting building materials before they're installed. And then we have shear strength. That's the third kind of strength. It refers to a material's resistance to being twisted. Again, see how different this is from compression or from tension. Materials with high shear strength require a structure with strong triangular cross-bracing in 3 dimensions like a trestle bridge. It's not enough to have strong bonds in 1 dimension like a rope, because a rope can twist and turn easily. And it's not enough to have strength in 2 dimensions like a stack of paper. Again, there's virtually no resistance to twisting a stack of paper. But some materials are extraordinary in this regard, and the structure of diamond leads to exceptional shear strength. Remember the diamond structure again. It's not just strong, it's strong in 3 dimensions, and all of its bonds are strong. It has this trestle-like arrangement, so it has tremendous shear strength. By the way, that's also why diamond is so hard. Now, it's important to remember that these 3 kinds of strength don't always go hand in hand. Remember, a stack of paper is tremendously strong under compression, but it's easily pulled apart under tension. And by the same token, a nylon rope, it's exceptional tensile strength, but virtually no compressive or shear strength. And here's an interesting example. The relative strength of a soft drink can depend on whether it has liquid inside it. Now, look at this. Here's a Coke can that's full, and it can support my entire weight. I can stand on this can. Although I don't want to push my luck for too long here. But if you take an empty can, it's the same external, it's different. If I try to stand on that, it crushes immediately. So it's got very low compressive strength. And also, you know, you can take a Coke can and just twist it in your hand. Almost no shear strength. Now, in many applications, a combination of these 3 different kinds of strength is essential. These considerations come particularly into play in designing structures to withstand earthquakes. See, earthquakes shake a building in several different ways, up and down and side to side, and a really nasty twisting motion as well. So think about the 3 different kinds of strengths. In an earthquake, a building needs to be both compressive, have compressive and tensile strength to withstand that up and down motion, but also needs shear strength because of the twisting and side to side motions. Now, masonry buildings are especially subject to damage because even though they have great compressive strength, masonry is very poor in terms of tensile and shear strength. Even relatively mild earthquakes can collapse solid masonry structures. Collapsing masonry buildings is one of the reasons why so many people die in some earthquakes. But you can design around this problem by using a variety of composite materials, including reinforced concrete and plywood. These materials dramatically increase a building's combined compressive, tensile, and shear strengths. And the use of such materials is a big part of the revised building codes in earthquake-prone parts of the country, like in California. All right, the second physical property I want to look at is thermal expansion. That's the tendency of materials to change their dimensions when they're heated. Thermal expansion is another property that's intimately related to chemical bonding. It's common experience. Most materials, they expand slightly when they're heated. You know, if you have a metal screw cap that's stuck on a glass jar, you can often loosen it just by putting that cap under hot water. The metal cap expands, and that loosens the seal, and then you can take off the lid. In materials like a bar of metal, atomic vibrations cause atoms to bump into each other, and they push apart slightly, and so as the temperature increases, so does the intensity of these collisions, and this increased force pushes the atoms apart, and the entire material expands. So thermal expansion is a pretty important property to measure. After all, if you're designing a bridge or a building, it's essential to know how much metal beams are going to expand on the hot summer days or shrink on the coldest winter nights. Thermal expansion also, it turns out, plays a central role in the behavior of the Earth. You see, when rocks get very hot, as they do deep in the Earth, they become relatively soft and they expand, so they become a little bit less dense. And that leads to an amazing phenomenon. The so-called solid rocks that make up our planet actually start to convect. They act essentially like a boiling pot of water. although it's on a much larger scale and a longer time frame. So a lot of scientists, myself included, have spent a good part of their research lives measuring thermal expansion of materials. One of the most remarkable aspects of thermal expansion, at least I think this is fascinating, is that a few materials actually have negative thermal expansion. That is, you heat the material up and it shrinks. Now think about how that might be possible. It seems paradoxical. The answer lies again at the atomic scale. See, these compounds have three-dimensional frameworks of extremely strong ionic bonds. And those ionic bonds act like rigid sticks, so the structure is kind of locked into place. Each atom-to-atom linkage is like a solid bar. And what happens at higher temperatures, the atoms vibrate more and more vigorously, so the angles between the bonds bend more and more. The angles between pairs of atoms are much more flexible. I can actually show you this with a simple device. See what I mean by this. This device represents three atoms. For example, two silicon atoms at the end and an oxygen atom right at the middle at the joint. Now at low temperature, the two silicon atoms are pretty far apart. And these represent two rigid bonds that have a constant distance. But as the temperature increases, this angle varies more and more as the thermal vibrations increase. And what that means is that on average, the distance between the two silicon atoms is less. They're closer together. And the result is a net thermal contraction. Even though the distances between the bonded atoms, the silicon to the oxygen to the other silicon, those distances don't change, but the distance between the two silicon atoms does get smaller. The theme of this lecture is that the properties of materials are the result of its atoms and the bonding. The close ties between atomic scale structure and physical properties are especially evident in the interesting property of stickiness. That's the third property I want to consider. We want certain materials like inks and glues and tape to stick, but we also want other surfaces such as frying pans and our car's windshield to be resistant to sticking. So this property is a direct consequence of bonding at the surface of a material. You see, sticky substances feature groups of atoms at their surface that readily bond with other substances. So think about that. Why would a material want to form new bonds? It has to have something to do with the outer electrons. You design a material in which the exposed atoms for some reason want a different number of electrons. There are lots of good adhesives known because it's fairly easy to design a substance in which at least some external atoms are eager to bond to other atoms and lock onto them. What represents a bigger current challenge in chemistry is to invent non-stick surfaces. For example, can you imagine a paint-like coating that's designed so that graffiti won't stick to it? Spray paint just beads up and rolls off it. You could just rinse a painted wall surface clean. That would be so great. For such a material to be effective, the outer layer of atoms has to look to the rest of the world like a layer of inert gas, which bonds to nothing. So the outer exposed atoms must have completely filled shells of electrons. And it turns out that there's a new group of fluorine-bearing compounds related to Teflon that may fill this need. I heard about these new paints a couple years ago, and I'm still waiting to see if there's a market version that comes out. But it's a really exciting possibility. Okay, another physical property is magnetism. Permanent magnets possess the ability to attract iron and other magnetic materials. And you know how this works. You take a magnet, and it has this interesting property being able to pick up iron objects and other magnetic objects. Now this kind of magnetic phenomenon seems to be a bulk property. All the magnets we use are big affairs. So what do atoms have to do with it? But once again, it turns out that atomic scale behavior lies at the heart of this physical property. Recall that it's moving electrons cause magnetic fields. And you can wind a coil of wire, of copper wire, and pass a current through it, as in a buzzer or a bell. And these are electromagnets. A magnetic field arises because an electric current travels in a curved path. But now think about an individual atom. Electrons, essentially in orbit around the atom, are in effect tiny electric currents. A single electron in an atom can produce a tiny magnetic field. In many atoms, the movements of different electrons effectively cancel. They go every which way, and there's no net magnetic field. But in some atoms, like iron, the electrons combine, and the atoms act like tiny dipole magnets, with a north and a south pole. It's just like a little electromagnet. The magnetic behavior of a material depends on the alignment of these individual atomic magnets. So in a ferromagnet, like the permanent magnet you just saw, many atoms may align to produce a large dipole field, and you get a refrigerator magnet. Now, magnets are often made by cooling an iron alloy or a nickel alloy or cobalt sometimes in a strong magnetic field. As the metal cools, all the atoms tend to align in the same direction, and the field is frozen in to that refrigerator magnet. The effectiveness of that magnet can be reduced or destroyed either by heating it in the absence of a field, or you can strike it repeatedly with a hammer. Those violent actions disturb the atoms lose their common alignment, and so the magnet doesn't work anymore. Well, now that you know how a magnet works, I have to tell you about one of the most common uses for magnets. That's in microphones and speakers. Think about what happens when a magnetic material is itself subjected to a magnetic field. See, every atom is a tiny magnet, so a force is exerted on every single atom. That means the atoms have to move slightly. A solid magnet actually changes its shape slightly in this situation. So by the same token, just doing this in reverse, if you change the shape of a magnet, the magnetic field must vary. But remember what happens when you vary a magnetic field. You get a varying electric field at the same time, and that lies at the heart of microphones and speakers. You see, in some kinds of microphones, sound waves cause a magnet to change its shape. The magnet's put against a kind of diaphragm. This change alters the magnetic field, and that in turn produces an electromagnetic signal, and that signal carries information about the sound waves. Okay, the fifth and last material property I want to discuss is electrical conductivity. That's the ability of a material to carry an electric current. One of the most important properties of materials in modern life is their ability to control the flow of electricity. We use this property all the time. Electrical conductors and insulators are both essential to this process. After all, you have to be able to move electrons in some directions, and you want to stop them from moving in other directions. And we saw that good electrical conductors include all materials in which electrical charges flow easily. Electricity, after all, is just the flow of electrons, and the most common conductors, therefore metals, which by definition have electrons that are free to move under the slightest voltage. It's true that all known materials have some resistance to electricity at room temperature, which causes heating of wires, it causes a loss of electrical energy. Skinnier wires get hot a lot faster, but this happens in any wire. Nevertheless, electricity can flow for many, many miles through copper wires without severe loss, so power plants can be built very far away. Now, most household electrical wire uses copper. Sometimes aluminum is used inside the walls of your house, and gold and silver are superior conductors, and they find specialized uses in various applications in electronics. And then there's also a growing class of materials that are called fast ion conductors. These fast ion conductors are finding special applications, especially in batteries. See, these materials have atomic scale channels. They're sort of like pipes for atoms, and ions, those are charged atoms like sodium or lithium. They can flow under an electric field. Once such a battery runs down, it's often possible to recharge it by passing current through in the opposite way. Another frontier occurs in organic chemistry. A lot of polymer scientists are trying to develop conducting polymers that might someday replace metal wires. It would be so cheap and easy to have wires synthesized from raw materials like water and plants. If you had a highly conductive fiber, then you'd have carbon-based wires, and they could eventually prove to be a lot cheaper and also lighter weight than metal wire. Now, on the other side are insulators. Insulators are essential to restrict the flow of electricity, and for safety and efficiency, we have to have these. You couldn't use electricity if you didn't have insulators. The best insulators are materials in which electrons don't move easily. We saw earlier that ionically bonded materials make the best insulator because there just aren't any free electrons. Every electron is assigned to a specific atom. Glass and ceramics, for example, the bonds between silicon atoms and oxygen atoms hold on to every available electron. And you may have seen those old glass or ceramic insulators from power lines. They're sitting up there. But plastic with covalent bonds, they're not quite as good insulators as ceramics. That's because electrons aren't quite as localized as in ionic bonds, but plastics are more than adequate for low voltage situations like we find around the house. And in many ways, plastics are a lot better. First of all, they're easy to shape into just about any size or shape. They can be colored to match any decor. And plastics can be made flexible, because in wiring you have to have flexible insulation. And so in modern wiring in your home, of course, you have plastic insulation wrapped around the conducting metal wires. Okay, there's one other aspect of electrical conductivity I want to tell you about. That's superconductors. Superconductors are remarkable materials. These conduct electricity without any resistance at all. Even the best metal conductors like gold have some resistance to the flow of electrons. If you start electrons moving in a loop of gold wire and turn off the voltage supply, the electrons just stop moving. Electrons collide with other electrons, the energy is dissipated as heat, and it doesn't work. But in superconductors, it's different. Set up a current in a loop of superconducting material, and that current will flow forever. It sounds almost too good to be true. And actually, in some ways, it is too good to be true, because it turns out that all these materials require extremely cold temperatures to work. But as new materials are being discovered, this temperature limit rises. Superconductors are finding many new applications. This phenomenon of superconductivity was discovered by the Dutch physicist Heike Kamerlingh-Onnes in 1911. He measured zero resistivity in a sample of mercury at 4 kelvins. Onnes is one of the world's great authorities on extreme refrigeration. Those are temperatures near absolute zero. And he found that once an electrical current started in his supercooled mercury, the current kept flowing for years without stopping. Such a property, this electricity without any resistance, it immediately had scientists and engineers imagining all sorts of practical applications. See, without heating from the current, you could build immensely powerful permanent electromagnets. Ordinary electromagnets are limited because they get hot and the wires start melting. Another application was electrical power transmission over very, very long distances without any loss at all. Wires are good, but still a lot of electrical potential energy is lost in transmission. So when the energy comes from the power plant to your home, you're paying for lost energy. And in this it might be possible to build electric storage rings. You see, it's most efficient to run power plants, especially hydroelectric plants at dams, 24 hours a day. But people use more electricity during daylight hours, and so a storage capacity would be great. So a lot of people began to work on superconductors. Most subsequent research focused on finding other superconducting metals, because mercury at 4 kelvins wasn't a very practical material. And eventually, all this research resulted in an alloy of the metal niobium that conducts at about 22 Kelvin. Now that's chilly, but you can use liquid helium as a refrigerant. Now liquid helium is pretty expensive, but it's safe and it's relatively straightforward to use. So niobium alloys, they're now used widespread in all sorts of high-power electromagnets for all kinds of applications. And you're most likely to run into one of these at a medical imaging facility that uses magnetic resonance imaging, or MRI. At the heart of that MRI machine is a powerful superconducting electromagnet. Once the electric current starts, the magnet is kept cold, and that current keeps flowing forever. Superconductivity is really a rather mysterious process. The most convincing theory of how this works involves the formation of pairs of electrons that in effect surf along electromagnetic waves as they themselves they set up themselves. It's sort of a weird idea. It's not an intuitively obvious process, and it's really been proven difficult to plot any effective strategy to design new superconducting materials, since we don't really understand where superconductivity comes from. A lot of work in this area has been termed cook and look chemistry. That's just a lot of trial and error. You try lots of materials and see what happens. It was in 1986 that the first of an amazing new class of superconductors that works at much higher temperatures was discovered. This breakthrough took place in a couple of steps. The first was made by two scientists working for IBM in Zurich, Switzerland. That's Carl Alex Müller and Johann Georg Bednorz. They defied conventional wisdom by looking for superconductivity in ceramic materials with ionic, not metallic bonding. And they set the world record with a copper oxide that was superconducting at about 30 kelvins. This discovery, it won them the Nobel Prize just 2 years later, and it set off a scientific gold rush. Thousands of scientists all over the world eventually dropped everything. They searched for higher temperature superconductors. But at first, not many people paid attention to the announcement. An exception was a friend of mine, a guy named Paul Chu at the University of Houston. He'd been working on developing new superconductors for decades, and he immediately set out to work on this new class of copper oxide materials. And within a few months of the Bednorz and Müller announcement, Chu and his own colleagues made a spectacular discovery, a spectacular breakthrough of a superconductor that at an astonishing 93 kelvins. That's high enough to use cheap liquid nitrogen. Now, for the first time in history, you could actually demonstrate superconductivity in an ordinary classroom. And I want to show you one of the amazing effects of superconductivity with one of these copper oxide superconductors. I'm going to pour some liquid nitrogen to cool this black wafer of superconductor down to liquid nitrogen temperature. It takes just a couple of seconds for that to cool. And while that's cooling down, I've got a small magnet here, and I'm going to place this magnet on top of the disk. And what you'll see is as the superconductor cools down, that magnet suddenly, look at that, begins to levitate magically above. It's floating against the force of gravity. This phenomenon could actually have some pretty remarkable applications. People have talked about magnetically levitated trains that travel hundreds of miles an hour on a cushion of air. And this demonstration really brings back memories for me. Back in February of 1987, I was contacted by Paul Chu to determine the identity of this black stuff. I'll never forget that phone call. I'd only met Paul once, and I was immediately taken aback because he said that he was about to discuss something to me that had to be kept secret. And that's not the usual protocol, at least not in geology. Then he told me he needed to have me determine a crystal structure. I said, what is it? And then he came back with a bombshell. He said, I can't tell you, but it superconducts at 90 kelvins. Now, that's a phone call you don't forget. Here is the problem. Paul and his team had made the black superconductor. They knew it worked, but they didn't know its exact chemical composition or its atomic structure. So remember the theme of this lecture. The properties of material depend on its atoms and how those atoms are linked together. So determining composition and structure was a big deal. It's interesting why Paul Chu contacted me. You see, all this was top secret, a discovery potentially worth billions of dollars. Paul needed someone who could solve the structure of a mineral-like material, but who wasn't in the superconductor game. So the geophysical laboratory where I work was the ideal place for the project. So we get this sample by FedEx. So immediately a group of 4 of us begin to work on it round the clock. And it turns out the sample was polycrystal, and there were thousands of tiny crystals. We had to mount up these crystals and X-ray them. And eventually we found one large enough to do the structure analysis. It turns out that the crystal structure was related to an important group of minerals called perovskites. We also found that the composition had a pleasing 1:2 to 3 ratio of the elements yttrium, barium, and copper. And here's the structure. It's just an absolutely gorgeous structure featuring layers of copper and oxygen atoms. It now seems that this layering plays a key role in the mechanism of superconductivity. And still, I think it's safe to say that no one is exactly sure how these superconductors work, and there's a lot of research that's still being done. There are lots of other layered copper oxide superconductors that have been found, at least 20 distinct structure types, and the highest temperature so far is about 150 Kelvin, which means that superconducting magnets and motors and other devices could be used on the moon and in other objects in space. And it's only been a dozen years since the discovery, so who knows what we're going to find. It's a big part of the excitement and the joy of science is what we don't know. To summarize this lecture, we've seen the close connection between a material's physical properties and its atomic structure. We looked at the strength of materials. We looked at the thermal expansion of materials, the stickiness of materials. We've looked at various kinds of magnetic properties, and finally electrical conductivity. All these are the result of the atoms and how they're linked together. But in the next lecture, we're going to continue this theme and look at electronic materials that have been changing our lives.